Acho que estamos prontos para começar a última plenária desse colóquio. Very good. Good afternoon, everyone. So I have the pleasure of introducing the last speaker of this colloquium, Professor Jelani Nelson from UC Berkeley. So Jelani Nelson studied mathematics and computer science at the MIT as an undergraduate, and so he stayed at the MIT for his master's and PhD, where he was a member of the Theory of Computation group, where he did brilliant work on efficient algorithms for massive data sets. Professor Nelson has held postdoctoral positions at the MSRI, Princeton University, and the Institute for Advanced Study in Princeton. He joined the computer science faculty at Harvard University in 2013, and then he joined UC Berkeley in 2019. So Professor Nelson is best known for his contributions to streaming algorithms and dimensionality reduction. I would also like to add some other aspect of his contributions. So Professor Nelson founded Coder, a summer program teaching computer science and algorithms to high schoolers in Ethiopia. The program has trained over 500 alumni, some of whom have gone on to study at prestigious institutions such as Harvard, MIT, and Columbia, just to mention three. Professor Nelson also co-founded the David Harold Blackwell Summer Research Institute, which aims to increase the number of African-American students receiving PhDs in mathematics. So finally, of his awards, I'll just mention one. So Professor Nelson received the 2022 ACM Eugene L. Lawler Award, and the citation reads, for his founding and developing Coder, a non-profit organization which teaches programming to underserved students from all over Ethiopia. Before I just finish, let me mention that so Jelani is a multi-talented person. So if you look on YouTube, you can see him typing. So he's a touch typist who can type more than 200 words a minute. He's also a very accomplished coder, and so he has participated in many coding competitions in all stages. And I just learned that he speaks Japanese. So he offered to give this lecture in Japanese. But I said that maybe that's not a good idea. So Jelani today will talk about sketching algorithms.
All right, thanks everyone. So yes, I'll talk about sketching algorithms. Thanks for the introduction and thanks for inviting me. Let's just start with what sketching algorithms are. By the way, can you hear me? Okay, good. So we have data and we want to answer some family of queries about that data. And a sketch is really just a compressed data structure that allows answering those queries. Okay, so a sketch is a data structure. And sometimes we want to answer queries across different data sets, like, how different are these data sets, how similar are they, and we want to be able to do it just from those data structures, from those sketches. As mentioned in the intro, I've also done a lot of work on streaming, and you can think streaming is just sketches that you want to be able to update dynamically as the data changes. So for anyone in the audience who does computer science, it's basically dynamic data structures, if you know that term. If you don't know, that's fine. But when we say streaming and sketching, the implication is we want to use very little memory, so we don't want to remember most of what we saw. Benefits, there's some obvious ones: less storage, faster, because if it's using less storage, it can fit in faster cache or memory. And if you're doing distributed computation, like if you have data spread across many different servers, and you want to independently compute on each and then merge the results, sometimes that can get you bandwidth reduction in communication because you only have to pass around sketches, not the actual full data sets. So just so we're on the same page, I'm going to give you a very, very simple streaming, in fact, example. But you already know how to do this. You didn't need me. In fact, a child could do this. So let's say that you're a website that sells stuff, Amazon. You have a stream of transactions with prices. Query is, what are the gross sales for the day, okay? Very simple, keep a running sum. That's your data structure. And it's very memory efficient, right? Even you don't have to remember every single transaction you saw for the day to be able to give the gross sales. You just need to keep one number in memory, and that one number is enough to be able to answer the query, okay? So the rest of the talk is going to be some examples that are not so simple. And in particular, I'm going to go over 4 examples: approximate counting, quantile estimation, sampling and graph streaming, and something called heavy hitters, or finding frequent items in data streams. So let's start with the first one, which is approximate counting. So very simple problem. This is maybe the first math problem that we teach babies to solve, when they're like 2 or 3 years old, which is literally count, okay? So the problem is maintain a counter n subject to 3 operations. Initialize the counter to 0, increment the counter, and query what is the value of the counter. That's it, okay? So literally the first, I think, problem we ask babies to solve. And the goal is to use as little memory as possible in bits, okay? And the straightforward solution, of course, if you have a number that's up to n, it has log n digits or log n bits to represent that number. So the goal is to do better than that, okay? So can you do better? And the answer is no, you can't do better, okay? So this is like, if I promise you that the number is between 1 and t, you need log t bits to store it by pigeonhole, okay? But it is possible if you slightly modify the problem statement in a way that still makes sense. So for example, let's say that our value n got to be super duper big like this. I promise you that this is a 728 digit number. Just take my word for it. So you would need 728 units of memory to remember this number. But in fact, if you're willing to remember the number approximately, just remember 3 things, 7 to 8. Just remember the number of digits, okay? And if you remember the number of digits, you still know the value of the counter approximately. You know it up to a factor of 10, right? Because the smallest it could be is 1 with a bunch of zeros, and the largest it could be is a bunch of 9s. And you say, okay, well, I don't want to know it up to a factor of 10. I want to know up to 1% error. That's fine. Just take the logarithm base 1.01 of the number and round that to the nearest integer and remember that. And that's still not that many digits. That's only 6 units of memory, right? But this is not, even this is not a solution to the problem on the previous slide. Why is it not a solution? Yeah, it's not updatable. We have to support increment. If the only thing I remember is the number of digits, and you say increment, did the number of digits increase? Maybe. I don't know, because I don't actually remember the number, right? So this would work if I kind of had the full number ahead of time and you told me to compress it. But it doesn't give me a solution to the dynamic problem where the number can be updated, okay? So Morris came along, a guy named Rob Morris in the 70s, and he gave the first algorithm to solve this problem. He was at Bell Labs. Before, at some point also in his career, he was chief scientist of the National Security Agency, our basically spy organization in the US. And why did he want to do better? Log n is actually pretty small. You're never really going to deal with numbers in the real world that are bigger than a trillion. Log base 2 of a trillion is roughly 40. So 40 bits. My computer has terabytes of memory. Who cares about 40 bits, right? So why did he care? And the original motivation is described in this survey by Lombroso. And basically, in the early days of computing in Unix, Morris wanted to implement a spell checker to automatically detect typos. And in fact, his spell checker was called Typo. That was the name of the program. And one funny thing about typo is it had no dictionary. It didn't look up words in the dictionary to see if there was a typo. It was purely kind of statistical. So it would look over the text. It would look at all trigrams, which are sequences of 3 characters at a time. And it would count trigrams. How many AAAs did I see? How many AABs did I see? There are 26 cubed possible trigrams. It would count all of them in your text. And then it would somehow do some kind of analysis to figure out what it thinks might be typos based on trigram distributions, okay? And the thing is, I guess in the computer that he had access to back in the 70s, if he had to fit 26 cubed counters, his memory at the time was only big enough to devote 8 bits to each of those counters, and 8 bits can only count up to 255, right? from 0 to 255. And that wasn't enough. In some of the texts that he was analyzing, some trigrams occurred more than 255 times. So he needed a way of approximately counting. And it was a randomized algorithm. I'll tell you roughly how it works in a moment. But the kind of the property it had was, so what I've done here is I implemented Morse's algorithm. And 5,000 times independently, I did the following. I picked a random number that was between 50,000 and 100,000. Okay, so that's about a 16, 17-bit number. And then I ran Morse's algorithm with only 8 bits. So I only gave it half the memory it really needed to count up to that number. And then I just kind of looked at what was the error produced by Morse's algorithm when I queried. And what you see here is an empirical CDF, basically, of the error. So the y-axis is the relative error. The x-axis is the percentile. So right at the 50th percentile, you see it's about 8% relative error. So about half the time, the median error was about 8% relative error. And the max error, the 100th percentile, was basically never more than 50%. So it never had more than 50% error. And the typical error was around 8%. So, did OK, giving it only half the memory to count up to a 16, 17-bit number. So it works decently well. How does it work? So let me tell you how it works. Oh, and that's back in the 70s. We have better computers today. So what's the current motivation? Who cares about Morse counter today? And I found out, I looked into this. I found out that it still gets used. In fact, it gets used in Redis. Redis is the most popular in-memory database open source in-memory database that people use. And I found a talk on YouTube of a software engineer who contributes to Redis. And one of her slides, she was explaining how Redis uses the Morse counter. And the bottom line is, it's kind of similar in spirit to why Morse was using it in typo. Yes, 30 bits or 40 bits for one counter is not a big deal. But Morse didn't have one counter. Morse had 26 cubed counters, right? So even though it's a small number multiplying a very big number. And so I want a smaller multiplier. So it's the same thing in Redis where, I won't spend time getting into the details, but in their implementation, they store a lot of counters for something. And if you can reduce the amount of space per counter, it's a win. So they don't really care about one counter. They care about lots of counters, and they implement each one using a Morse counter. Okay. So let me explain how Morse's algorithm works. And the first idea is, of course, to use randomness. It's a randomized algorithm. And you have to be randomized if you want to beat log n bits. You can prove that, even if you're approximate. And you're not going to store your actual counter n in memory. You're going to store a different number x. And when you say initialize, you're going to set x to 0. And whenever a user increments n, what you do is you flip a coin. And if the coin is heads, you increment x. If the coin is tails, you do nothing. OK? So what's the idea here? Well, you expect to increment x only half the time. So x in expectation is n over 2. So when someone says query, you just return 2 times x. That's correct in expectation. OK? And basically what that means, I still approximately know n, but I'm only storing a number half as big, so I saved a bit of memory. OK? Now, this is not his algorithm. His algorithm does something a little more fancier than this, but kind of what's the downside? What are the downsides with this solution? One is that you only save 1 bit of memory. I'm trying to save a lot of memory. And the other is that the error is actually quite terrible for small n. Imagine that n is 1. You only incremented the counter once. X will then then your first coin flip will either be heads or it will be tails, which means x is either 0 or 1, which means you'll return either 0 or 2, which means you're off by 100%. Okay? So when n is small, your error is actually kind of guaranteed to be bad. Okay? So let's fix the first issue, which is you only save 1 bit of storage. Let's save more bits of storage. So whenever a user increments n, instead what we'll do is we'll flip x coins. X is the current value of our counter we're storing. And I'll increment x only if all of the x coins are heads. So basically, I increment x with probability 1 over 2 to the x. You can show, it's not hard to show that in expectation, 2 to the x is n plus 1. So if you want an unbiased estimator of n, compute 2 to the x minus 1. That's an unbiased estimator. But that means that usually x is typically around log n. And what you're storing is x. Storing x takes log x bits. So your memory now is like log n. You've exponentially improved your memory, okay? And in fact, if you think about it, that's the thing where I showed this 728-digit number, and I said, just remember 728. I mean, 728 is log n, right? So that's kind of performing similarly as that solution, but with a dynamic, but supporting dynamic updates. The problem is that your error is still terrible for small n. Okay, so then here's the kind of finishing touch of Morris. So on the one hand, Morris was incrementing with probability 0.5 to the x. The trouble, I mean, the great thing was that the memory was low. The trouble is that there's high variance, and it kind of messes up my error. On the other hand, I could increment with probability 1.0 to the x, which is just like what children do. And then I have no variance, but then my memory is high. Okay? So you look at this, and there's a very natural thing to try, which is like, what if I increment with probability 0.99 to the x? Okay? And you can show that, then a good way to estimate n would be this formula that I wrote up there. Where does that come from? It comes from the fact that if I increment with probability 1 over 1 plus a to the x, or think of a as something small, a is 0.01, the expectation of 1 plus a to the x is an plus 1, so I can basically figure out an unbiased estimator from that. Compute 1 plus a to the x, subtract 1, divide by a. That's an unbiased estimator. And you can show that this unbiased estimator has variance, which is a times n choose 2. In particular, as a goes to 0, the variance goes to 0. And if you just do second moment method, it implies that if you set a to be something like epsilon squared times delta, then you'll get 1 plus epsilon multiplicative relative error with probability at least 1 minus delta. And your memory ends up being log n plus log 1 over a. It's concentrated around that. So you get memory which is log n, which is good. Log n is basically remembering the number of digits, plus log 1 over epsilon plus log 1 over delta bits, proportional to that number of bits. That turns out to not be the end of the story. A couple of years ago, with my former postdoc, now he's a faculty member, we showed that this bound is actually not optimal. In particular, the dependence on delta is wrong. There is another algorithm which gets dependence on the failure probability log 1 over delta, which is iterated. And furthermore, we can prove a theorem that this is the best possible up to a constant factor. There is no algorithm that does better than this memory. Okay? Log n plus log 1 over epsilon plus log 1 over delta. Okay? Just information theoretically. It's impossible to do better. And at first when we realized this, we had a new algorithm. We were very excited. We implemented our algorithm. We implemented Morris. We compared them. And they performed basically the same. And then we showed that if you just slightly tweak Morris itself, slightly tweak the algorithm I just showed you, the slightly tweaked Morris also gets this bound. The original Morris does not, but the slightly tweaked Morris does get this bound. And then I got very excited because I was like, people actually use Morris in real life, like Redis. I went to the GitHub page for Redis. I posted something, and then I got a response, which is like basically like, we're busy. we don't have time to implement new algorithms. Maybe in the future. That was like 5 years ago, so probably it's low priority for them. Anyway, so that's that. I didn't have time to show you kind of the details of the new algorithm, the new upper bound, and how do you prove that there's nothing better. But I think rather than do that, I'd prefer to show you just more examples of sketching and streaming since I only have an hour with you. So let's do another problem, which is quantiles. So this is a screenshot. I mentioned OddDecoder. So OddDecoder has an Instagram page. And we posted a video a couple days ago. And one thing that Instagram has is like analytics for users, where you can look at how many people watched your video, what's the average watch time, how many people watched it past the first 3 seconds, basically analytics for content providers, okay? So, so for example, real, when I say real, I mean like video reels, video reel analytics on Instagram, are able to answer questions like, what is the median watch time of my post? Like, for how long did the typical user watch my post? How about at the 75th percentile? What if I'm Google, for example, and I want to know what is the 99.9th percentile latency for a search query response? Okay, because I want to make sure that my service is performing well, and most users are not suffering long latency times to get their answers. Okay? So the problem, basically, is I see a sequence of integers. Those integers could be the lengths of time users watch my video. They could be the response time to a search query in milliseconds. I see a sequence of n integers from some bounded range, 1 to u. And then later I see quantile or rank queries. A rank query is, given x, return the number of elements I saw in the stream that are less than x. And I allow some error. The answer you give me can be wrong up to an additive error of epsilon n. Or select, which is basically quantile. So you give me an r, return an element whose rank is r, plus or minus some error epsilon n. So for example, quantile queries are basically select queries, right? So if I say 75th percentile, then r is basically 0.75n, right? I'm doing a select on 0.75n. So what are some bounds for this problem? And the folklore bound is just sampling. So if I want to know approximately how many people are less than some query x, if I just sample like 1 over epsilon squared elements from the stream, and then answer based on the sample, then just by second moment method or Chernoff bound, Hufting, whatever, I'll get the correct answer up to plus or minus epsilon n. So the folklore result is just sample 1 over epsilon squared things from the stream. There was a paper in almost more than 20 years ago, Srivastava et al. They gave a data structure called the Q digest that had memory 1 over epsilon, not 1 over epsilon squared, times log u, words of memory. There's another paper that's more recent, 9 years ago, by Karnan, Lang, and Liberty, that got 1 over epsilon times log 1 over delta memory, where delta is the failure probability, so it's a randomized algorithm. And only very recently, last year, Gupta, Singhal, and Wu, two of them, they're all grad students at Berkeley, 2 of them are my advisees, showed an algorithm that's deterministic 1 over epsilon words. And there have been many other algorithms in this space over the years. I'm kind of not putting all of them. But there's something remarkable about the last row, which is this bound of 1 over epsilon words is the best possible, even if I gave you the full database up front and said, compress this database so you can answer queries later. Just like when I said with the approximate counting, even if I gave you the full number up front and I said, compress it so that you could tell someone else the answer, the thing to do is remember the number of digits, basically, right? Or remember the logarithm base 1.01 of the number, or the logarithm base 1 plus epsilon of the number, rounded. Similarly here, even if I gave you the full stream of elements up front and I said, I want you to later be able to answer any quantile query, what you should do is sort the items and store the elements at ranks epsilon n, 2 epsilon n, 3 epsilon n, and so forth. And then later, when someone queries, you just round to the nearest multiple of epsilon n. And you can prove that that's the best you can do. And what's the memory there? It's 1 over epsilon, because that's how many multiples of epsilon there are between 0 and 1. And kind of the remarkable thing about their algorithm is they match that bound up to a constant factor, even though they don't know the full database up front. They have to basically maintain a data structure on the fly as things are getting updated. And I'm not going to be able to show you their algorithm. There's some complications, but I'll maybe start you off in the direction of understanding their algorithm. And really, the starting point of their algorithm is the Q digest from more than 20 years ago. And I won't write any code. I'll show you what the Q digest is by picture. And by picture, let's say U is 16. So your universe is all the integers from 0 to 15. Okay? Imagine having a complete binary tree on your universe. Of course, we're not going to store this because that would use too much memory, but just imagine for a second you have that. And imagine that every node, whether it be a leaf or an internal node, has some capacity to store items, but limited capacity. And in this picture, the capacity is going to be 3. Okay? And it's not even going to store the item. It's just going to store a counter of how many items are there. So I see the item 5. What I want to do is I want to kind of walk down the tree to 5 and increment the 5. But what I'm going to do is, as I'm walking down the tree, the first node I encounter that is not full, I'm going to put the 5 there. And of course, the first node that I encounter walking down to 5 is the root. And the root is not full, so I'll put the 5 in the root. Now I see the next number in the stream, which is 11. I want to walk toward 11. The first node I encounter that's not full is the root. I increment the root. Then I see another number 7. I walk towards 7. So now the counter at the root is 2, right? I walk towards 7. Oh, the root's not full. I can put the 7 there. Now white for me means full. So now that I see 1, I can't put it at the root because the root is full. So I walk toward 1, and I put the 1 in the first node I encounter that's not full, which is that one. And then I see 11. I walk toward 11, put it in the first place that has room, which is the right child of the root. 14 goes there as well. And then, after some number of insertions, the tree is evolving. And basically, the idea of the QDigest is, the capacities of these nodes, don't make them 3. Make them epsilon n over log u, okay? Something. And if you set it to be that way, what you can prove is, so kind of what's the intuition? The intuition is later if someone says, what's the rank of 11? Okay? What's the rank of 11? What do? I start at the root, and I walk toward 11. And every time I go right, every time I go to a right child, I know everyone in the left subtree has to be smaller than 11. So I should add it in. So I walk toward 11. Oh, that left thing, all of that must be less than 11. Let me add it in. And then there I walk left, then right again. Oh, that white node must be less than 11. I add it in. And the point is, all the nodes on the path, all the white nodes on the path, I don't know whether those elements that live there are bigger than 11 or less than 11, because they kind of got captured higher up. So those are my sources of error. And because I set the capacities to be epsilon n over log u in each node, the total error is epsilon n over log u times the depth of the tree, which is log u. So my total error is epsilon n. So that's kind of how it works. And you can show that, it's just a calculation that because of the way I'm doing things, I'm never going to have more than log n over epsilon active nodes in this tree. The number of nodes in this tree that are not empty is never more than log u over epsilon. So that's my memory. My memory is just store the active nodes. Log u over epsilon nodes, that's my memory. And kind of the main idea of the paper from 2024 is, if you look at the set of active nodes, it's a contiguous subtree containing the root. And yeah, like the bottom nodes, the leaves in this contiguous subtree might not be full, but all the internal nodes are full. And remembering the tree structure of the internal nodes actually is efficient. The thing that kind of dominates the memory is storing the counters at those leaves. So what you do is you basically store the tree structure on the white nodes very efficiently, and then you treat future insertions as being insertions into gray nodes, the leaves that are hanging off the contiguous subtree. But the gray nodes themselves, there are not that many of them. There are only u prime of them, where u prime is proportional to log u. So essentially what you've done is you've reduced your universe of size u down to a universe of size roughly log u, and then you use recursion. You basically recursively deploy a data structure that handles insertions into these gray nodes. And there are log star u levels of recursion, where log star is this iterated logarithm, how many logs you have to take to get down to 1. Okay, and then now things get messy and complicated, and that's where all of their work happened. But I'll just leave it at that. Okay, so that's kind of the highest level idea of how this thing worked, and it's completely deterministic. And if you're clever like they were able to get this down to an actual optimal solution, kind of based on this idea. So I'm done with 2 examples, 2 more, okay? And this one actually is a little interactive. You're going to play a game with me. Do people like playing games? I hope. Yeah? Okay. Okay, good. So here's the game. One of you is holding a basket of fruit. And initially that basket of fruit is empty. At every time step, I can take a fruit and put it in the basket, and you watch me do it. Like you see, I'm holding an orange, I put the orange in the basket. You see me do that. Another thing I can do is I can look in the basket and take a fruit out, okay, of my choice. The thing that's not allowed, and you see what I take out. The thing that's not allowed is you are never allowed to look inside the basket yourself. Now, in principle, you should know what's in the basket because you see what I put in, and you see me take things out. But the point is, you have bounded memory, right? So how can you do this when you have bounded memory? And the thing that I want you to be able to do is when I say query, you don't have to tell me the entire contents of the basket. All you have to tell me is one fruit that's still there. So if there are 20 different fruits that are still in the basket, just tell me one. Okay? If you can do that, you win. Okay? So let's play the game together. Okay? So now the basket is empty. I just put a strawberry. You see me, right? You see I put a strawberry. Everybody sees that. And then I put a watermelon. And then I put a grape, an orange, peach, banana, peach. Okay, oh, you saw that? Okay, let's just go back. So I put a peach, I put a banana, I put a second peach, right? So there are two peaches. I'm allowed to put multiple of the same fruit in. But then I removed a peach. But there's still one peach left, right? Good. Oh, but I removed the second peach. So now the second peach is gone. So I keep inserting things, and you're seeing it. Like there's nothing secret. You're going to see everything I do. And then at some point, I might start deleting fruits, right? Okay, so let's see. Now I'm starting to remove fruits from the basket. So there are no secrets here. You're watching everything as I'm doing them. And then at some point, I'm going to ask you, tell me something that's still there in the basket. Okay? Banana. Mango, kiwi. Come on, I mean, there's a lot of you in this. Someone has to know, right? So I promise you there's actually two things in the basket, and it's a plum and a lime. There's one of each left, okay? So that's the problem. The problem is, I'm going to rephrase it a little bit. Maintain a vector in a stream. It's an n-dimensional vector subject to this kind of update operation. I give you a coordinate. I give you a delta, which is an amount. Add delta to that coordinate. So in this case, delta was always +1 or -1, right? So you can think n was the number of types of fruit in the universe. Whenever I inserted a fruit, that was delta as 1. Whenever I removed a fruit, that was delta as -1. Z was basically the histogram of all the fruits. And query is just give me any index that's in the support of the vector. Any I such that Zi is non-zero. There are applications of this. There are a lot of them, especially for graph problems. So An, Guha, and McGregor showed more than 10 years ago that if you have a good support-find data structure, you can use it to do dynamic spanning forest in a graph. So basically, you have a graph on V vertices, and you're allowed to insert edges, you're allowed to remove edges, and then query is give me a spanning forest of the graph. Okay? And here n, the number of fruits, the size of the universe, was basically V choose 2. So it was like a histogram over edges that could possibly be in the graph. So whenever you're inserting an edge E, you can think that you're actually adding 1 to this V choose 2 dimensional vector in one of the entries, in the Eth entry. Okay? And as you can imagine, so why is it useful? Basically, there's like, forget about spanning forest, just like tell me an edge that's still in the graph. It's non-trivial, right? Like just like the fruit game. If you're going to give me a spanning forest, you have to at least give me an edge that's in the graph. Okay? So good. And there were several other works that not only said give me something in the support, but give me a random thing in the support. And what should the distribution be? Again, you could have multiple peaches in your basket. So this Z histogram, some of the entries are not just 0 or 1. They could have multiplicity. And let's say I want you should return the ith item with probability proportional to Zi or proportional to Zi squared or some kind of function of Zi. Okay? So for different kinds of distributions, people looked at different ways of doing it. The state of the art for support find is there's failure problem. It's a randomized algorithm. And the memory is log 1 over delta times log squared n bits to succeed with probability 1 minus delta. That was in 2011. And for LP sampling, where the weight function is proportional to Zi to the p, it was shown that this log squared n bound is also achievable. And since Onguha and McGregor found that application to dynamic spanning forest, it's found applications, the same data structure has found applications to lots and lots of graph problems, from cycle freeness, simulating random walks, disjoint paths, matching problems, vertex cover, minimum spanning tree, k-connected components, and so forth. Some of these algorithms need the sampler version. Some of them only need support find, but all of them are using this kind of technology. And maybe I'll just tell you, how does the algorithm work? Okay, how do you do it in log 1 over delta times log squared n bits? Okay, and of course, the naive thing you might say is like, let me just sample. Right? Let me just sample from the stream, but that doesn't work because someone can insert an item a billion times and then delete it a billion times and then insert just a couple other items, and you have to figure that out, right? And of course, this could all be interspersed. So here's an idea, and it's related to compressed sensing in a way, sort of. Suppose I had a data structure D which solves the k-sparse recovery problem. That's a different problem. K-sparse recovery is, if Z has support size at most k, tell me Z. If Z has support size larger than k, the algorithm is allowed to misbehave arbitrarily. Okay? So suppose I had such a data structure, and then I'll show you how to use that data structure, and then I'll show you how to implement the data structure later. So what I'm going to do is I'm going to pick a random function, h, which maps the set of all fruits, 1 to n, into a range of size log n, such that the probability that hi is j is 1 over 2 to the j. And I'm going to instantiate log n independent copies of that data structure, d1 up to d log n. And here's what I do. And there's also going to be a d0. Okay, but so whenever I see an item in the stream, someone inserts a fruit. They inserted a strawberry. I'll apply my random function to strawberry. It's going to give me a random level between 1 and log n. Most things go to 1, right? Because the probability that you go to j is 1 over 2 to the j. So half the things go to 1, a quarter of the things go to 2, and so forth. So it'll go to one of these levels, probably one of the higher levels. But some things might go to the bottom level. Okay? And if you want to do support find, you want to recover an element of the support, here's basically what you do. Let's say the support size is s. In expectation, how many items from the support get mapped to the bottom data structure? S over n, right? Because the probability that you get mapped there is 1 over 2 to the log n, which is 1 over n. So in expectation, s over n things map to the bottom level. Okay? And maybe s is much less than n. So typically, maybe nothing maps to the bottom level. If you go one level higher, how many things map there? 2s over n, right? And one level higher, 4s over n. At some point, if you're working your way from the bottom upward, you'll get to a level where 2 to the L s over n is not small anymore. It starts being at least 1. Go to the level where it starts being, where 2 to the L s over n is roughly log 1 over delta. By Chernoff Hoeffding, if you expect log 1 over delta there, you will have roughly log 1 over delta there with high probability, with probability 1 minus delta. Okay? And then, if you query that data structure, it'll report it to you because it's sparse. That's it. That's the whole thing. Okay? So the total space is log 1 over delta levels times, log n levels times the space per level, and the space per level turns out to be k log n. So that's why you get k log squared n, which is log 1 over delta log squared n, which is what I told you. How do you implement this data structure D? If you think about it, so what we're going to do is we're going to pick a linear map pi. So now this is solving that problem. If you have a vector whose support size is at most k, how do you recover it? So let's call that vector x. X has support size at most k. I need to recover it. What I'm going to store in my memory is pi x for some matrix pi. How should I choose a matrix pi such that, given pi x, I can recover x for any k-sparse vector x? Well, if you think about it, I just need the map x map to pi x to be an injection on the set of k-sparse vectors, which means for all k-sparse x not equal to x prime, pi x had better not equal pi x prime, which means x minus x prime had better not be in the kernel of pi. Okay? So x is k-sparse, x prime is k-sparse, x minus x prime is 2 k-sparse. So basically what I want is I want a matrix pi such that if you look at any 2k columns, okay, it has full rank. Okay, so I'll choose this, which is basically like a transpose Vandermonde matrix. If I take any 2k columns of this matrix, I basically have a Vandermonde matrix still, and I'll set M to be 2k minus 1. I get it, so I'm done. Okay, so this thing has that property, and that's what I'll use. Okay, so that's it. That's the algorithm. Good. And how do I use that? So now that I have that, how does this get used in graph algorithms? For example, how did Ongu and McGregor use such a thing to do spanning forest in a dynamic graph? So before I tell you that, I'm going to show you kind of an algorithm that I want to simulate. And I'll show you how I'm going to describe an algorithm. I'm going to describe then how to simulate that algorithm using support find. So here's the algorithm. It's going to run in phases, in rounds. Every round, I'm going to ask every vertex, tell me an incident edge upon you. Boom. 1 told me 1, 2. 2 told me 2, 1. 3 told me 3, 1. Every one of those vertices is telling me an incident edge upon him, which is this red edge. And then what I'm going to do is I'm going to simultaneously contract all those edges. So these red ellipses are me contracting all those edges and getting super vertices. So now I have 3 super vertices. Now I'm going to do round 2. Every super vertex, tell me an incident edge upon you. That one has no incident edges upon it. These, the 4, 5 super vertex told me 1, and the 6, 7 super vertex told me 1. I contract. I'm done. And now so now I know the connected components, and what is my spanning forest? All edges that I contracted. Of course, that's not a forest, but in post-processing, I can just remove cycles. Okay? So that's the algorithm. Now, how do I use support find to implement that algorithm? So what I'm going to do is each node in the graph I'm going to imagine has associated with it a v choose 2 dimensional vector. So there are v vertices. Each one has a v choose 2 dimensional vector. That sounds like a bad idea. That's v cubed memory. Just storing the graph would take v squared memory. So this seems like I'm going in the wrong direction. But what I'm going to do, okay, and also, if I have an edge, which is the AB edge, if I look at the eth entry of ZU, well, if U is not A and U is not B, then I'm just going to define ZU E to be 0. Otherwise, if one of the endpoints is U, then I'll either make it -1 or +1, depending on whether the smaller vertex is U or the larger vertex is U. So that's how I define these ZU vectors. And then, this is the magic, I will remember now, the support find solution that I showed you, at the end of the day, was a random linear map. Right? There was some hashing going on. When I hashed to one of these D data structures, that thing was a Vandermonde matrix. If I just stack all these Vandermonde matrices on top of each other with some, basically the whole thing is linear. The whole thing is a linear map. So I can think of the algorithm as a linear map. So I'm going to pick capital R copies, one for each round of the previous algorithm I showed you, one for each round of this process, I'm going to pick a random independent support find data structures. Each one is a linear map. And what I'm going to store in my memory is not the ZU vectors, but that matrix times ZU, where that matrix is a solution to support find. And how many matrices do I need? Log V, basically the number of rounds. And there's never going to be more than log V rounds, because if you think about that picture I showed you, every round, kind of the number of connected components basically halves, right? Or the number of super vertices that are left to be merged halves. So after log V rounds, I'm kind of done with all my contractions. And this is the magic. So in round 1, when I ask every vertex, tell me an incident edge, I'm just querying each one of those data structures. Vertex 1, tell me an incident edge. Vertex 2, tell me an incident edge, right? Then I find them. Now I need to merge, I need to contract those edges. How do I contract an edge? sum the vertices in the set. If S is a supervertex, if you sum all the ZUs inside S, then if A and B are both within the supervertex, the A side will be a -1, the B side will be a +1. When you sum them up, they zero each other out. So when you sum up the ZUs, the support that's left are the edges that actually leave the supervertex. And because this data structure is linear, I can get pi times the sum by just summing up the corresponding sketches. And that's it. So basically, every round, I identify which things got contracted. I sum up the corresponding data structures for those things. And the supports, the edges that are within that supervertex zero each other out. And what's left in the support are edges that leave that supervertex for the next round. That's it. OK. And the truth is that actually this solution I showed you for support find is optimal. So in 2017, I was able to show with Kaprilov and others that any data structure which solves support find has to use log1/delta times log squared n bits of memory. Okay, it's information theoretic. There is no solution, no matter how clever you are, that's better. Okay. The bound is asymptotically tight for all ranges of parameters. And then later with Hua-Cheng Yu, I was able to combine this with what's called the direct product theorem in communication complexity. Let me not get into that right now, to prove that the Ahn-Guha-McGregor algorithm for spanning forest is actually optimal. In particular, if the thing you want to solve is dynamic spanning forest, there is no solution that uses less than v log cubed v bits of memory. If you think about it, if there are no deletions, the problem is easier, right? If I just tell you, like, here's a graph on v vertices, it starts with no edges, and I'm going to insert edges one by one. Tell me a spanning forest. How much memory do you need? V log v. Basically, every time you see an edge, if it bridges two different connected components, remember it. If it doesn't bridge two different connected components, throw it away. It's useless. Okay? And then what's your memory? Well, your memory is at any point in time, you're remembering a spanning forest. A spanning forest has no more than v minus 1 edges, so your memory is v log v bits. And what we showed was if you have to support deletions as well, so not only edge insertion, but also edge deletion, any algorithm needs v log cubed v bits of memory. There's a log squared v bit overhead to being able to support deletions. And it was built on this lower bound for support find. And Hua-Cheng Yu later showed that even in the distributed model, you can imagine a different model that's not streaming but distributed. What do I mean by that? Imagine a model where every vertex knows its own neighbors, and that's all it knows. And there's a central computer that can receive messages, and based on those messages, compute a spanning forest. How short of a message can I get away with? Every vertex has to send a message. I want each message to be short. The naive thing is each vertex would send its neighborhood to that server. But its neighborhood could have v minus 1 other vertices. So that would be messages of length v minus 1. It turns out that you can implement this algorithm so that each message is actually only length log cubed v bits. And what Hua-Cheng showed is that that's optimal. There is no distributed protocol where vertices can get away with sending fewer than log cubed v bits. You need to send at least log cubed v bits, even on average, from a vertex to that central computer, for that central computer to be able to construct a spanning forest. I think I want to skip the rest of this and move into my last example, because we're running low on time, which is frequent items. And that's the last one I have for you before, I guess, we're done at 1. So what is finding frequent items? So here's a fake search engine query log from last night. And lots of people have the word wiki in their search. Okay. So I want an algorithm which basically watches these searches coming in and watches all these words and could answer for me what are the frequent words that are being searched. So problem, given a stream of items, such as words coming from a universe like the English dictionary, at query time, report a small list of words containing all the frequent words. Frequent depends on some input parameter, let's call it k. And let's say the stream has L items. K frequent for me means it appears more than a 1 over k fraction of the time. So tell me any word that appeared more than 1% of the time in the stream, for example. If I say 1%, there can be at most 100 such words. Okay. The trivial solution is to use a number of words of memory which is proportional to the size of the English dictionary. Basically, keep a histogram, right, where the indices in the histogram corresponds to words in the dictionary, and whenever you see word I, increment the ith entry in the histogram. And the goal is to use much less memory than that. Okay? So again, I can phrase this in terms of this, what we call turnstile streaming, where there's a high-dimensional vector z that starts as 0, and they have coordinate-wise updates. So for example, if I see a word that's a +1 update, you can imagine another application where I might want to be able to delete from the database. That's a -1 update. And then a query asks for some function of this histogram. In my case right now, I care about the frequent query, which is return a list containing all the heavy hitters, all the frequent items that appear more than a 1 over k fraction of the time. And this list should have bounded size, O of k. So the definition I just gave you of being a heavy hitter is that zi is bigger than a 1 over k fraction of the sum of all the z indices. Maybe I should have said j there. Sorry for that. So frequent says output a subset of the universe that's bounded size and contains every heavy hitter. You can define the heavy hitter problem a little bit differently. Instead of saying that zi is bigger than the sum of all the other zij's over k, you could say maybe zi squared is bigger than 1 over k times the sum over j of zj squared. So it's not a 1 over k fraction in an L1 sense, it's a 1 over k fraction in an L2 sense. You could define it that way. If you define k heavy hitter in a way like that, where you say, look, I want zi squared to be bigger than 1 over k times the sum from k plus 1 to n of zj squared, where the z star vector is sorted. So basically, z star is the decreasing rearrangement of z. So z1 star is the largest entry of z, z2 star is the second largest entry of z, and so forth. And if you let the weight function be the p of power, it's not hard to prove that as you send p to infinity, someone is a heavy hitter if and only if they're in the top k. Okay? I mean, that's a natural thing to ask. Give me the top item in the stream. Give me the top 10 items in the stream. That's the top k problem. And what this note is saying is, if you use this LP version of the problem and you set p to be large, it becomes the top k problem at some point. So if the thing you really want to solve is the top k problem, you should solve this problem with p as large as possible. Although, some bad news, if p is larger than 2, solving the LP version of the problem requires polynomial space. So larger p is better. It's a better approximation of top k. But if p is too large, if it's larger than 2, it's basically not doable in small memory, which means that the best you can hope to do in small memory is p equals 2. OK, so just keep that in mind. And with that in mind, there has been a lot of work on this problem over the years. Again, a folklore thing you can do is just sample. If someone is frequent in the stream, if you sample, you'll probably still see them. But you can actually do better than sampling. And in the insertion-only version of the problem, the state of the art is the BP tree, which was in 2017, the work I did with Braverman et al. It's a randomized algorithm for the L2 version of heavy hitters. And amongst all L2 heavy hitters algorithms, it has the best known memory. And in particular, the first algorithm for the L2 version of the problem used k log n memory. This is to find the approximate top k in this L2 sense. Then there was something called the count C, which used k log log n memory. And our BP tree uses k log k memory. K is always less than n, so k log k is always better than k log n. And it's still to this day an open problem whether you can get away with k memory. So can you do approximate top k in an L2 sense with O of k memory? We don't know, but we know how to do k log k. And in the last few minutes, I'll try to give you a flavor of how that algorithm works. Remember, our goal basically is identify indices I with zi squared larger than that thing on the right-hand side. If you want, you can ignore this decreasing rearrangement thing and just think zi squared is bigger than 1 over k times the L2 norm squared. Have that in mind, okay? That's also good enough to think about. And the way our algorithm works is we first define a notion of superheaviness. So instead of saying zi squared is a 0.1% of the total L2 mass, say actually zh squared is 99.9% of the total L2 mass. In an L2 sense, zh is almost everything. C is like 1,000. Zh squared is 1,000 times bigger than everyone else squared. Okay? So what we do is we show algorithmically how to reduce the original problem into identifying a superheavy index if one exists. And then we show how to solve the superheavy problem. And what we show is if you can solve the superheavy problem in space S memory, you can solve the original problem in S times k log k. And then we show how to solve superheavy in constant memory. We show how to solve superheavy in like, I don't know, less than 10 words of memory or something, right? Constant number of words of memory. So there's two pieces. One is the reduction. How do I reduce the original problem to superheavy? And one is how do I solve superheavy? Reducing the original problem to superheavy is via some hashing trick. Let me skip that for now, for the sake of time. And let's just focus on how do you actually solve superheavy. And to solve superheavy, we make use of a core lemma. And the core lemma says the following. Suppose you have this vector z, this histogram, that's evolving in a stream. And the evolution is y at time 0, y at time 1, y at time capital T. So y is the frequency vector, this histogram that's evolving. And of course, if it's evolving in a stream, what it means is from one step to the next, you added 1 to some index. Right? That's what it means. That's the evolution. You added 1 to some index. And suppose you choose a random Rademacher vector sigma with independent, well, here I say 4 y's independent entries, but even say they're independent entries. And let's look at the expectation over sigma of the max over time steps t of sigma dot yt. Then this expected maximum is bounded by a constant times the L2 norm of the final vector. Okay, that's the lemma. That's the core lemma. And the proof sketch is we do some Dudley-type chaining with 4 y's independent tail bounds. Are people familiar? Anyone seen Dudley's inequality or generic chaining? Anyone seen chaining here? Okay, some people, maybe not everyone. That's fine. Abstract that away. Okay, I'm not going to get into it in this talk. And just an example of like this lemma in action. Imagine the stream being 1, 2, 3, 4, 5. Those are the things I see in the stream. Then after t time steps, the frequency of item 1 is 1, the frequency of item 2 is 1, the frequency of item 3 is 1. So yt is t1s followed by a bunch of zeros. And then if you look at sigma dot yt, it's this prefix sum of sigma 1 plus sigma 2 plus dot dot plus sigma t. It's the position xt of a random walk on the integers starting at 0 after t time steps, right? Where at each time step you go left or right with probability 50-50. And we know from like maximal inequalities, like Levy's inequality kind of stuff, that after capital T time steps, the max deviation from the origin ever is bounded by a constant times root capital T. Notice that, I mean, at time t, you're roughly at root t, but the maximal inequality says you never deviate by more than a constant factor times that in the middle. If you're naive and do a union bound, you're going to lose a factor of root log t. The maximal inequality, the beauty of it is you don't lose anything. Okay. So this core lemma generalizes the maximal inequality. And why does it generalize it? Well, the maximal inequality follows as a corollary. But the core lemma can handle an arbitrary evolution of the stream, so you can have the same token repeated. And furthermore, you're walking on the integers. Normally in maximal inequalities, your increments are independent over time steps. Here, increments are not independent. In our proof, the sigma I only needs to be 4 y's independent. They can be pseudo-random and it still holds. Okay? So now, how do you make use of that core lemma to design an algorithm? Wishful thinking. Suppose you knew the final L2 norm of the frequency vector exactly at the beginning. You don't, but suppose you did. Okay? And because there's a super heavy person, the final L2 number at the end is basically almost the same as the frequency of the super heavy person at the end. Because in an L2 sense, he's almost everything. Let's say that capital H is the ID of the super heavy item. We'll try to learn capital H bit by bit. Capital H is a number between 1 and n, so it's a log n bit number. We'll try to learn those log n bits one by one. So how do we learn the 0th bit? We'll draw a random sigma from a 4-wise independent family, and I promise I'm almost done. We'll instantiate 2 counters C0 and C1. Whenever we see an item in the stream, we look at the 0th bit of that, because we're trying to learn H0. So 14 in binary is 1110. It ends in a 0. We add sigma 14 to C0. That's what we do. So note that at some point in the stream, let's say that the super heavy item actually ends with a 1 in binary. It's actually odd. Then C1 will be plus or minus the frequency of the super heavy item plus all the other people who happen to also end with a 1 in binary times a random, dotted with a random sign vector. And C0 is everyone who's even dotted with a random sign vector. And basically, what the core lemma says is that those 2 blue sums are small. They're noise. Because in an L2 sense, ZH is almost everything. And the core lemma says that those blue sums are proportional to the L2 of that noise. But the L2 of that noise is dominated by ZH. So essentially what happens is at some point, we realize that C1 is very large. Therefore, the super heavy item must be in C1. Therefore, the super heavy item ends with a 1 in binary. And then once we learn that, we then try to learn the next bit and the next bit, and then it gets a little more, there's a little more steps there that I'm not going to get into, but that's basically how it goes. And one thing that I didn't say, but I should say is, why do we care that the sigma is 4-wise independent? Because again, we're memory bounded. If sigma were actually fully random, it would take n bits to store sigma. We don't have n bits. We're trying to use a bounded memory algorithm. The beautiful thing is I can generate 4-wise independent random bits, n 4-wise independent random bits using only O of log n bits. So the beauty there is by generating pseudorandom random sign vectors, I can get away with less memory, and that's very important for the design of the algorithm. So I think now I'm out of time, and I'm also out of slides. So I'm happy to take any questions.